Let's take a look at understanding the concept of a singularity in complex variables in terms of like a picture, for example. So imagine we have f of z equals 1 over z. We need a function where we have division involved, because that's what introduces the possibility of division by 0. And then imagine z is x plus yi. That's a complex number, x plus yi. So now imagine we have this point, and this is going to be the origin. So call it, say, the following, 0 plus 0i. We want to see what happens when we approach that point in terms, for example, of the outputs of 1 over z. So how can we do that? Well, grab a point. Now, complex numbers are often represented by little arrows, for example, but not only. You want to grab a point that's very close to 0 plus 0i. So we'll make one up, say, and because we're only on the horizontal axis, it's only a real number. So, for example, imagine it's 0.1, okay? And now look at the output. What do you get from the output? So you'd have f of 0.1. That would be 1 over 0.1. That would be equal to 10. So look at what's happened here. I'll do this kind of off to the side in a separate system so you don't get confused. Okay, again, this would still be 0 plus 0i. So again, I'm just doing this in a separate system because I don't want to have too many arrows in one. Then it becomes messy. But the point is, you see, if this arrow represents 0.1, then when it goes into 1 over z, which is 1 over 0.1, you get 10 out. So you get an arrow that's much bigger. You see this? I mean, let's say this is not to scale. It doesn't have to be. The point is that this is 10. Now it's all the way out. Compare the size of the arrows, roughly speaking. See? All right. Let me move this down. So I'm going to need more room, definitely. Okay. Now, let's do this again. So grab, say, another number that falls along this axis. So that would be, for example, like 0.1i, because it's going along the imaginary axis. And do the division and see what you get. So f of 0.1i, you'd have 1 over 0.1i. So you can separate this as follows. It's 1 divided by 0.1. Do that part first. That's 10 over i. Okay, and then you can multiply by I over I because that's 1. So it's going to give you 10i. Yeah, 10i like this. All right, finish. 10i over I squared by I squared is negative 1. So it gives you negative 10i, you see? So taking and plugging in 0.1i gives you negative 10i. You can imagine that that's represented, say by an arrow that goes all the way down this way. Hold on. Like imagine that's negative 10i right here. See, the point is that this is negative 10i. As you can see, because you're plugging in 0.1, by the time you finish the division, you get a number that's pointing in the opposite direction, and then on top of it, it's much bigger, right? The modulus is much bigger. The length of it is much bigger. All right. Then we continue. So grab another complex number. So this one, just the real part, because we're again along the horizontal axis, so that would be negative 0.1. And then do the division. So, and now you have to be careful because you see it's hard to keep track of all the calculations sometimes in the right place. So f of negative 0.1. So 1 divided by negative 0.1 is going to give you negative 10. Okay. So that means that's the number that gets sent over to here, you see? This is negative 10. So that goes here. Now let's finish. Let's grab from the bottom the complex number that says negative. Okay, so negative 0.1i. Carry out the division. So f of negative 0.1i, that's going to be the following. 1 divided by negative 0.1i. So work this out. So 1 divided by negative 0.1 is negative 10 at first. That's the numerator. And then it's over I, but then you multiply by I over I and you simplify. So because that's 1, standard procedure. Let me punch this down below here. So you're going to have negative 10i divided by I squared. So you're going to end up therefore with negative 10i over negative 1, which is positive 10i. So look, this negative 0.1i gets imaged into this number right here. Positive 10i. Right here, you see? 10i positive. So these numbers that are very close to 0 plus 0i, once you divide them into 1, as you can see, they actually produce numbers that get stretched away from the origin. So that's one way to think about a singularity. Okay, you can imagine that, like, if I took numbers like in this location here, right, and a number in this location here, and a number in this location here, and a number in this location here. So like say half of 0.1, half of negative 0.1 I, half of negative 0.1, half of 0.1 I. If I took each of those and I fed it into 1 over z, the outputs would be bigger still. So this is one way to think about it. The image, so to speak, as you approach the origin, the image from the division produces complex numbers that tend away from the origin. Okay, so that's one way. Another way you can think about this is as follows. Well, since you have the number x plus yi, but this is our input, don't forget. So our output would be 1 over x plus yi. Now, in general, since x plus y is kind of like the arbitrary input, then 1 over x plus yi is kind of like the arbitrary output. It's what you get from the division process. What we want to know is, for example, the length of these. It makes sense to do this calculation. This is just a complex number in the end, right? So like you see, for each division that I did here, what was produced was just a complex number. So this is just in the end a complex number, so you can find its length, its modulus. Okay, so how do we do it? Well, here it does help if we first do this. Do x minus yi, and then over x minus yi. So this is allowed, it's not arbitrary, because this is just a form of the number 1. You're allowed to multiply by 1. But then you produce from this process x minus yi, and then let's see, it's going to be divided here by, well, in the bottom you're going to have x plus yi times x minus yi, so hopefully you know by now that it's just x squared plus y squared, that kind of setup, okay? All right, so then you can split it into the real and imaginary parts. Therefore, you're going to have x over x squared plus y squared, and then minus y over x squared plus y squared, and then I. So this is equivalent to the original, even if it looks different, it's not. Okay, so now look what happens, friends. Okay, very carefully. Let's apply the meaning of finding the modulus. You're going to have, in other words, x over x squared plus y squared squared by the Pythagorean theorem, because remember, each complex number, right, whatever goes in here, once you do 1 over it, you get a complex number, right? Even if it's at some angle, like this angle right here, that's just still an arrow, which means it still makes a right triangle this way, which means you can still use the Pythagorean theorem to find its length as usual, you see? Okay, that never changes. So you're going to have plus, and then y squared over x squared plus y squared. It's quantity squared. It's a Pythagorean theorem. I just worked with the algebra here, so it's going to be x squared plus... All right, and here I meant to say just y without the y squared, so let me fix that. Okay, sometimes I have trouble seeing what I'm writing on the screen. My eyes are not the best anymore. Okay, anyway, so x squared over x squared plus y squared, but the whole thing has to be squared by the rules of exponents. Okay, then you continue. Hold on, let me just turn on the light here. I feel like it's getting hard. All right. Oops. Sorry. 1 second. All right, move right in this light. That's probably better. There we are. And the next one, so y squared over... Let's do it this way. Yeah. So y squared and then distribute. So x squared plus y squared quantity squared. This is just all algebra here. That's all it is. So you're going to have x squared plus y squared over... And look, x squared plus y squared quantity squared. Now cancel off x squared plus y squared between numerator and denominator because they repeat. So all you will have left, in fact, is 1 over x squared plus y squared, and you can distribute the root symbol. So you have a root of 1, which is just 1 over the root of x squared plus y squared. But this here is just a function of x and y, correct? And if it's a function of x and y, then you can visualize it using a surface in three-dimensional space. Then it's just a matter of interpreting the points on it correctly in terms of the context. So let me show you a graphical representation, and then we'll talk about what this object represents and means and how to read everything in it, okay? Let me just make it a bit smaller if it frees it. So what is this surface telling us? So imagine I take a point, a random point from like the horizontal plane, x, y down below, which here you can kind of imagine is also like the real and imaginary. Let's say call this the real axis here, okay, RE for real, and then call this IM for imaginary. Okay, so then imagine you grab a point from there. I'll just represent that with a dot, for example. Let's say I do it over here or something like that, okay? Okay, so imagine I just grab the value of 2. Then when I form this quantity, remember our function's f of z equals 1 over z. Right? When z is just equal to 2, then we just have 1 over 2, correct? That's it. That's just a real output. So in that case, the length here from the real and imaginary plane down below to the surface right here, that length that you see there, that's equal to 1/2. That's just equal to the modulus of the number, you see? That's important to understand. So on the other hand, if I just grab obviously an arbitrary point, like whatever, say I grab, this is the imaginary axis, so 1, 2, say I grab something like this, that point, okay? Say that's the point 3i, like that, from the imaginary axis. So if you divide that out, you would have 1 over 3i, isn't it? Which you multiply by I over I, like this. So it's going to give you, in other words, I over, let's just work it, I over 3i squared. And then it's going to be I over -3. But when you take the modulus of this quantity right here, so kind of like this, correct? Like I over -3, that kind of situation. So that's just going to be give you 1/3. So it happens again that you would interpret this to say that from here to here is 1/3. Okay, 1/3, like this, that would be the length. And then take some other point, say from here, and then you would go through a similar calculation, and then the distance, from that plane essentially to like the surface itself, that would tell you the modulus of the number 1 over z, whatever this particular z happens to be here, okay? That would be the modulus up here. This would be the modulus of 1 over z. That's how you'd interpret the points along the surface. And notice that this shows something really important about what happens when we approach the origin. So if we approach it along this axis, look at what happens. The modulus, right, goes towards positive infinity. If we approach along this axis, the modulus goes towards what? Positive infinity, doesn't it? You see? If we approach along this axis, then the modulus goes up again towards positive infinity. And likewise, if you just approach, along any arbitrary directions, pretty much this way towards the origin, towards 0 plus 0i, which is what you would call the origin in this context, right? The modulus will grow towards positive infinity. So this kind of shows the singularity, but the singularity that you see kind of represents what happens to the length of 1 over z as z approaches 0. It explodes towards infinity. So symbolically, we'll say something like, essentially, as x plus yi approaches the point 0 plus 0i, then the modulus of 1 over x plus yi, something along these lines, approaches positive infinity. And that's how you can think about it. These are some ideas behind thinking about how visualizing, for example, complex numbers and singularities and so on. You could also see what happens besides this when you're taking numbers from a circle around the origin, but I think I will do that in a separate video. Or around some specific shape that you have around the origin, and then you see what happens when you shrink the shape towards the origin. What happens, for example, to the outputs. But that's enough for today, so leave a like. It's been insightful.